Across the silent expanse of our solar system, beyond the familiar orbit of Neptune, and far past the realm where the sun's light begins to fade, a lone spacecraft is still whispering back to Earth. Imagine a machine launched when disco was king and personal computers were a fantasy, now sailing through the cosmic deep at a distance so vast it defies ordinary comprehension. Its name is Voyager 1, and for 47 years and counting, it has been humanity's most distant ambassador, a robotic emissary sending messages home from the edge of interstellar space. Voyager 1's story began on September 5, 1977, when a Titan IIe rocket thundered off the launch pad at Cape Canaveral, hurling the spacecraft toward the outer solar system. Its mission was audacious, to visit the gas giants Jupiter and Saturn, capturing images and data no one had ever seen before. These worlds, shrouded in clouds and mystery, beckoned with the promise of discovery, and Voyager 1 delivered in spectacular fashion. As it raced past Jupiter, it revealed the planet's turbulent storms and volcanic moons. At Saturn, it sent back dazzling photographs of the rings and the enigmatic moon, Titan. But the real marvel began after Voyager 1's planetary encounters. Instead of shutting down, the spacecraft pressed onward, venturing into the uncharted territory beyond the known planets. As the years slipped by, Voyager 1 continued to hurtle outward at a speed of nearly 17 kilometers per second, fast enough to cross the distance from New York to Los Angeles in less than 4 minutes. Today, it is more than 24 billion kilometers from Earth, a distance so immense that even light, the fastest thing in the universe, takes more than 23 hours to cross the Gulf. In August 2012, Voyager 1 made history once again. Instruments on board detected a sudden shift. The sun's protective bubble of charged particles, called the heliosphere, had given way to the raw, ancient plasma of interstellar space. This invisible boundary, known as the heliopause, marks the true edge of our solar system, the place where the influence of our star fades and the vast expanse between the stars begins. Voyager 1 became the first human-made object to cross this threshold, sampling the conditions of the interstellar medium and sending back the first direct data from the space between the stars. Every day, the spacecraft drifts farther from home, now more than 160 astronomical units away, each astronomical unit being the average distance between the Earth and the Sun, about 150 million kilometers. The immensity of this distance is hard to grasp. When Voyager 1 sends a radio signal, that message travels at the speed of light for nearly an entire day before it reaches Earth. Commands from mission control take just as long to arrive, meaning every adjustment, every status check, is a conversation stretched across almost 2 days of round-trip time. The fact that Voyager 1 can still speak to us at all is a triumph of engineering. Its lifeline is a 3.7-meter high-gain antenna, a parabolic dish that must remain precisely pointed at Earth, despite the tumbling, shifting forces of deep space. Through this antenna, Voyager 1 transmits a narrow-beam radio signal using less than 20 watts of power, about the same as the light bulb inside your refrigerator. By the time these faint waves reach Earth, they are billions of times weaker than a typical FM radio station. Yet, thanks to NASA's Deep Space Network, an array of enormous dish antennas located in California, Spain, and Australia, even this ghostly signal can be amplified, decoded, and transformed into meaningful science. The Deep Space Network is a marvel in its own right. Each of its dishes spans up to 70 meters across, built to capture the faintest whispers from spacecraft at the farthest reaches of the solar system. When Voyager 1's signal arrives, it is little more than a flicker above the background noise of the universe, yet powerful computers and sensitive receivers tease out its meaning, delivering a steady stream of data about cosmic rays, magnetic fields, and the plasma environment beyond our star's influence. Powering Voyager 1 through this epic journey is a trio of radioisotope thermoelectric generators, or RTGs. Each contains a carefully shielded source of plutonium-238, which decays and releases heat. Thermoelectric converters transform this heat into electricity, providing just enough power to keep Voyager's essential systems alive. With each passing year, the output fades slightly, the plutonium growing colder and less energetic. Engineers back on Earth have orchestrated a careful dance of power management, shutting down heaters, deactivating non-essential instruments, and rationing every available watt to keep the most critical science packages running. Despite these constraints, Voyager 1's instruments are still at work. Its cosmic ray detector monitors high-energy particles from distant supernovae and galactic sources. The magnetometer measures the interstellar magnetic field, revealing how our solar system interacts with the broader galaxy. The plasma wave instrument, which first detected the crossing into interstellar space, continues to listen for oscillations in the charged particle environment, mapping the properties of the region humanity has never visited before. It is a testament to the vision of the scientists and engineers who designed Voyager 1 that, after nearly 5 decades, the spacecraft endures. Every transmission is a triumph, a pinpoint radio pulse, crossing 24 billion kilometers of emptiness, containing data that expands our knowledge of the cosmos. As long as its power holds out and its antenna remains locked onto home, Voyager 1 will continue to report from the frontier, a solitary outpost sending back humanity's most distant scientific dispatches from the space between the stars. Launched on September 5, 1977, Voyager 1 began its odyssey with a bold mission: to explore the farthest reaches of the solar system. Its primary targets were Jupiter and Saturn, giant worlds cloaked in swirling storms and encircled by enigmatic rings and moons. Voyager 1's cameras and instruments unveiled these outer giants as never before, capturing volcanic eruptions on Jupiter's moon Io and the delicate icy ringlets around Saturn. But these planetary encounters were only the beginning. After its Saturn flyby in 1980, Voyager 1 was set on a trajectory that would carry it away from the plane of the planets and out toward the edge of the Sun's domain. For decades, it journeyed through the distant reaches of the heliosphere, the vast bubble of charged particles blown outward by the solar wind. Scientists long theorized about the boundary that marked the end of the Sun's influence, the heliopause, where the solar wind's pressure balances with the thin gas of interstellar space. In August 2012, after more than 35 years in flight, Voyager 1 made history. Its plasma wave instrument detected a dramatic shift, a jump in the density of charged particles, accompanied by fluctuations in the magnetic field. This was the telltale signature of crossing the heliopause, the moment Voyager 1 left the Sun's protective bubble and entered true interstellar space. For the first time, a human-made object was sampling the environment between the stars, where the solar wind gives way to the broader galaxy. Today, Voyager 1 is farther from Earth than any other spacecraft, more than 160 astronomical units, or about 24 billion kilometers away. To grasp the scale, consider that 1 astronomical unit is the distance from Earth to the Sun. Voyager 1 is now over 160 times farther than that, receding at a speed of about 17 kilometers per second. Its signals, traveling at the speed of light, take nearly 23 hours to cross the Gulf back to Earth. Every command sent, every byte of data received, must traverse this vast, silent expanse, an extraordinary feat of communication and patience. Maintaining contact at such distances is possible only because of Voyager 1's 3.7-meter high-gain antenna. This carefully engineered dish projects a focused, tight radio beam, transmitting using just 20 watts of power, less than the light bulb in a refrigerator. Yet, across the void, NASA's Deep Space Network stands ready, a global array of massive radio dishes in California, Spain, and Australia. These dishes, each up to 70 meters wide, are capable of detecting Voyager's signal, now a mere whisper, billions of times fainter than the static from a distant radio station. When Voyager 1 transmits, The Deep Space Network's ultra-sensitive receivers capture the faint X-band signal, amplifying it so that computers can decode the stream of telemetry. Within this data are priceless scientific measurements: the flux of cosmic rays, the direction and strength of magnetic fields, the subtle changes in plasma density. Each transmission advances our understanding of the interstellar medium, the vast, diffuse region that fills the space between stars, shaped by supernovae, galactic winds, and ancient cosmic events. The challenge is not just communication, but also power. Voyager 1 draws electricity from 3 radioisotope thermoelectric generators, or RTGs. These nuclear batteries convert the heat from decaying plutonium-238 into electrical energy. But every year, the power output drops as the plutonium decays and the thermocouples degrade. In the early years, there was enough power for all of Voyager's instruments and heaters. Now, with less than half of the original energy, engineers have had to make difficult choices, shutting down heaters, turning off non-essential systems, and carefully rationing every watt to keep the most vital science instruments operational. Despite these constraints, Voyager 1's cosmic ray detector, magnetometer, and plasma instruments remain active, continuing to probe the galactic environment. The data they send back are irreplaceable. No other mission has ventured so far or sampled the interstellar medium in situ. The variations in cosmic ray intensity, the direction of the magnetic field, and the density of charged particles all help scientists model the shape of the heliosphere and its interaction with the galaxy beyond. The endurance of Voyager 1 is a testament to the ingenuity of its designers and the relentless dedication of the teams that still monitor its status. Each week, engineers check the health of its subsystems, upload carefully crafted commands, and adjust its operations as the power budget changes. After nearly 5 decades, the spacecraft systems, many built with 1970s technology, continue to function in the harshest of environments, exposed to cosmic radiation, extreme cold, and the relentless vacuum of space. As the years pass, the RTGs will continue to fade, and some instruments will inevitably be silenced. Yet, as long as a trickle of power remains and the high-gain antenna stays pointed toward Earth, Voyager 1's signal will persist, a faint murmur, but a real-time connection to the space between the stars. In the deep quiet of interstellar space, this spacecraft carries both scientific instruments and a golden record, a message in a bottle for any who might someday find it. But here and now, it bridges the gap between human curiosity and the vast unknown, transmitting data that may one day help us understand our place in the galaxy. Voyager 1's journey is not simply about distance, it's about crossing boundaries of science, of engineering, and of imagination. Every new reading from this distant outpost reshapes our models, challenges our theories, and inspires new generations to look outward. It is a living experiment, a testament to what can be achieved with vision, perseverance, and a relentless drive to explore. The signal endures, a beacon from the outer darkness, proving that even the most distant emissary can still teach us about the universe we call home. Yet, even as Voyager 1 drifts into the great unknown, its mission is far from over. Every hour, its instruments, designed decades ago, continue to sample the interstellar plasma, measure the direction and strength of magnetic fields, and detect high-energy particles sweeping through the Milky Way. These observations are crucial, for Voyager 1 is providing our first direct, in-situ data on the space beyond our solar neighborhood. Before its journey, everything we knew about interstellar space came from indirect observations, distant starlight, hints from cosmic rays, or theoretical models. Now, we have real measurements, a window into a realm that was once entirely inaccessible. The numbers alone are staggering. At over 24 billion kilometers from Earth, Voyager 1 is racing away at more than 61,000 kilometers per hour. its signals are so faint, so distant, that by the time they reach Earth, they're already more than 20 billion times weaker than the power required to run a digital watch. And yet, using the Deep Space Network's enormous radio antennas, each dish measuring up to 70 meters wide, NASA's engineers can still lock onto these whispers from the void. They must account for the motion of the Earth, the spacecraft, and even the subtle distortions caused by interplanetary plasma, just to ensure those crucial bits of data survive the journey. Inside the spacecraft, the countdown is ever present. The decay of plutonium in its RTGs gradually saps its electrical power. Each year, the total available wattage drops by a small but significant amount. To adapt, engineers have prioritized the most essential scientific instruments, shutting down heaters, cameras, and even, eventually, some of the legacy experiments that first mapped Jupiter's storms or Saturn's intricate ring system. What remains active is focused entirely on the new frontier: cosmic rays, magnetic fields, and the plasma waves of interstellar space. The challenges Voyager 1 faces are immense. Temperatures in deep space plunge to hundreds of degrees below zero. Cosmic radiation bombards the spacecraft from all directions, threatening to disrupt circuitry that was never designed for such an environment. The spacecraft's software, written in the 1970s, is still running on onboard computers with less memory than a modern calculator. Commands must be carefully crafted, tested, and timed, since every instruction sent from Earth will take nearly a full day to reach Voyager and another day before a response is received. Despite all this, the data continues to flow. By analyzing changes in the density of charged particles, scientists have discovered that the interstellar medium is not empty, but teeming with activity. Shock waves from ancient supernova ripple across the galaxy, occasionally washing over Voyager and triggering a surge of plasma oscillations, phenomena that were only theorized until these direct measurements. The spacecraft's magnetometer has shown how the sun's magnetic influence fades, giving way to the more complex and turbulent fields of interstellar space. Each new reading helps refine our models of galactic structure, cosmic ray propagation, and the protective bubble that shields our solar system from the wider galaxy. Looking ahead, Voyager 1's mission will eventually draw to a close. As the plutonium fuel decays, power will fall below the minimum needed to operate even the most basic systems. Science instruments will blink off one by one until only the faint carrier signal remains. Finally, perhaps in the next decade, that too will fade, and the spacecraft will silently continue its journey, an inert relic drifting endlessly between the stars. But even then, its legacy will endure. The data it has returned will fuel scientific discovery for generations, and its golden record, containing sounds and images of Earth, will travel on as a message in a bottle, a greeting from humanity to any who might one day find it. Voyager 1's Odyssey is a testament to what can be achieved when we dare to look beyond the horizon. Its enduring signal is a reminder that the boundaries of our knowledge are always expanding, and that even the faintest whisper from the farthest reaches of space can contain answers to questions we have only just begun to ask. If you've been inspired by the story of Voyager 1's incredible journey, make sure to like this video and subscribe for more content like this. The universe is vast, our curiosity is endless, and there is always more to explore.